So this is a 2000 paper question 23 on pressure and upthrust. So a sonar detector is attached to the bottom of a freshwater log. So it's a freshwater log, so that immediately tells you what the density is. The density you would get from the data sheet at the front of the booklet. You wouldn't be expected to remember it, but it's going to be 1000 kilograms per meter cube. The detector has a mass of 100 kilograms. At each end of the detector has an area of 0.4 meters squared. Atmospheric pressure is 101,000 pascals. The total pressure on the top of the detector is 108,350. Show that the total pressure on the bottom of the detector is 111,290. So we're asked to calculate that the total pressure on the bottom of the detector is 111,290. So in order to do that, we're going to use pressure equals rho GH. So density times gravitational field strength times H, which is the depth in this case. So the density of fresh water is 1000. As I said, you would get that from the data sheet. G is 9.8, and the depth to the bottom of the detector is, well, it's 0.75 to the top of the detector plus a further 0.3, so it's 1.05 is our total depth to the bottom surface, 1.05 meters. If you calculate all that out, you'll get 10,290 pascals. But you'll notice that that's not the answer here that you're looking for. That's where you've got to add in another element of pressure, because it says here atmospheric pressure is 101,000 pascals. So what the atmospheric pressure is the pressure that's keeping the top surface of that water flat. So anytime you've got juice or something inside a glass, the reason why the top of that top of the surface is flat is because there's atmospheric pressure pushing down on it. If there wasn't, then it would be moving about from the pressure that's inside the liquid that you're drinking. So you've got to add that value on. So anytime that you have atmospheric pressure, you have to include that as well, because imagine that we've got all these little molecules in here pushing down on the top surface of this object. We've also got loads of molecules in the air that are pushing down on the top surface of that water. So it's everything that's above that. So we need to add that on. It kind of makes it easy for you because it gives you the answer there, and just by looking at the numbers you could tell you would have to add that on. So your total pressure on the bottom surface is equal to 10,290 plus this atmospheric pressure of 101,000, and that will give you the number that you're looking for, which is 111,290 pascals. Now B, calculate the upthrust on the detector. So we're looking to calculate the force. We've already got pressure. We've got the total pressure on the bottom here. The total pressure on the top is given here as well. We also know what the area is, so we can just do a couple of simple calculations and then subtract the difference. So the force on the top is going to be equal to the pressure on the top multiplied by the area. The pressure on the top, as given in the question, is 108,350. And the area of this detector is 0.4. That will give you 43,340 newtons. So that's your pressure on the top. Force on the top rather. Force on the bottom is going to be the pressure on the bottom surface multiplied by the area, which is the same as before. Pressure on the bottom we've just calculated as 111,290. Area the same as before, 44,516. So there's a force difference there, just as there was a pressure difference. The deeper you go in a fluid, the more the pressure increases. So that affects the force. So we've got a greater force on the bottom surface than we do on the top surface. That's what's going to cause the upthrust. So upthrust is equal to the difference between these two forces. Now it's going to be the bottom force that is the larger number, so we'll put that first. So that'll be 44,516 minus 43,340. That will give you 1,176 newtons. That's your upthrust. Now C is more of an explanation question. The sonar detector is now attached as before, but to the bottom of a seawater lock this time. It's put in bold there just so you don't forget. The top of the detector is again 0.75 metres below the surface of the water. The detector is the same size, so everything else is the same. The only thing that you've really changed is the water that it's going into. So it's the seawater that we're looking at. How does the size of the upthrust on the detector compare with your answer in B? Well, what's changed here? The only thing that's changed here is that the density has changed. So the density of seawater, it's got lots of salt in it in addition to the water, so there's more particles there, so it's greater than the density of water, fresh water. So that's going to make the upthrust greater. So upthrust is greater. Upthrust is greater because density has increased. And if density is increased, if we go back to the start of the question, if this number is going up, and this value, density, G is always the same, height has stayed the same as before, so this pressure is going to go up. So you're going to have a greater pressure on both the top and the bottom surfaces. So you're going to have a greater pressure difference. Because density has increased, making pressure difference larger. And if the pressure difference is larger, that means that the difference between these two forces is also going to be bigger. So the upthrust is going to be bigger too. Resulting in a greater force difference. Or greater resultant force would be fine as well.